Hi, and welcome to my talk. My name is Eliel Camargo-Molina, and in the next 20 minutes, I'm going to tell you a little bit about our work in this paper. There, we consider the idea of having a first-order Electroweak Phase Transition in the standard model effective field theory, and in particular, a scenario that we think is very interesting phenomenologically. I hope at the end of this talk, I'm going to convince you of the same. So let's get going. First, as a bit of a motivation, I wanted to just point out this very interesting essay written in 1983 by John Ellis and Dimitri Nanopoulos about particle physics and cosmology. In there, it becomes very evident that the idea of probing this intersection between cosmology and particle physics has been drawing the curiosity and attention of physicists for a long time. In fact, we knew first from cosmology that there were only three neutrinos, and we only have an upper bound on their masses from cosmology today. It's a two-way relationship as well, because nuclear physics is crucial for star formation and abundances and understanding the early universe. So this is a very fascinating subject that has concentrated the attention of physicists. And I think we're reaching a point where we are going to be able to connect all of these ideas with robust experimental evidence and get finally some answers, concrete answers. When it comes to answers, right now, we have the idea of having two standard models. The standard model of particle physics with its field content and essentially a staggered theoretical success. And in the same way, we have the lambda CDM model that is able to set the grounds for an explanation of the history of our universe and how things work. And while they are in themselves staggering, as I said, theoretical successes, they're also the source of many open questions about fundamental phenomena. So I tried to collect here in this slide the open questions that I thought were most interesting. These as a way to illustrate the fact that there is a deep connection between all of these open questions. And not only a deep connection, but a connection that very often, if not every time, ends up leading you to the ideas relating to the vacuum of the universe, scalar particles, the scalar potential, and that possible answer might tentatively live in those ideas and in those sectors. So based on that, I've been interested in trying to understand how we can exploit that connection by understanding and studying the issue of phase transitions in the early universe and of course, the scalar potential. So before we dive into the details and the technicalities of our work, I wanted to just do a flyover the idea of phase transitions, just so that we can also set the language that we're going to be using during this talk, and also to remind ourselves of some of the basics. So I'll be very schematic, but in particle physics, when we talk about phase transitions, we refer to the transition from one vacuum and its associated symmetries and physical laws to another broken phase with other symmetries and other physical laws. So often we think about a universe at a very high temperature that was fully symmetric and had a potential that only had one minimum, that then started cooling down, and then the potential started changing with that cooling down until a point, a critical temperature, where you have a new minimum that develops at the same depth of the one where you are, and then two things can happen. What can happen is something like we have here on the left, where this new minimum, when the temperature gets lower, becomes lower than the minimum you are in, and then the phase transition goes kind of schematically again as a kind of classical rolling down this hill. But then what can also happen is what we have on the right here, which is that when that new minimum becomes lower, you still have a wall between the phase where you are and the phase that you will transition to. And this transition, in this case, that you have a wall, is going to go through quantum tunneling. And this is what people refer to when they talk about a first-order phase transition, or at least a way of seeing it. So the interesting part of a first-order phase transition is that it's one of the necessary ingredients for generating the baryon asymmetry that we observe in the universe. So, of course, it's not the only thing we need, and there's a lot of other conditions that have to be met. For example, baryon number violation, charge and charge parity violation, and a strong departure from thermal equilibrium. But nevertheless, if there's not a first-order phase transition, there's no hope for understanding this through this process called baryogenesis, which we're not going to dive into, but I just wanted to point the importance of the checking and understanding whether we had a first-order phase transition when it comes specifically to the electroweak phase transition. So this is when the SU2 cross U1 symmetry of the standard model gets broken down to the U1 electromagnetism symmetry that we observe today. And it's a very important example because whatever theory you have there, whether it's the standard model or something beyond it, the success of the electroweak theory tells you that this phase transition in some way or another happened in the early universe. Okay, so then of course is the question, you can think about what happened in the early universe and phase transitions and whatnot, but can we actually get some experimental evidence? Can we measure these and check whether our ideas and our models and our mechanisms actually happened? And the quick answer is that yes, and the long answer is that, well, this is a very exciting area that I encourage you all to start thinking about and working, of course. But the first thing that pops up is the idea of gravitational waves, right? So the early universe was transparent to gravitational waves, and a first order phase transition means that you have bubbles that nucleate. I'm always surprised that the analogy with boiling water holds up, but it's a good thing to think about. You have these bubbles with the new phase inside of them that expand at the speed of light, and they collide and disturb space-time massively. So this disturbance generates some stochastic gravitational wave background that could be in principle measured by an interferometer. So the next interferometer is the LISA interferometer space antenna that is going to be launched around 2030, thereabouts. And the question is, are we going to be able to measure the spectrum, or the spectrum in the frequencies that correspond to a hypothetical first order electroweak phase transition? And to answer that question, well, you start with a particle physics model, then you define some phase transition parameters that you can calculate given your favorite flavor of model. And then from that, you feed all those parameters into a very complicated, computationally expensive, and state-of-the-art numerical simulation of bubble collisions and sound waves propagation and things like that, until you get some spectrum that you can compare with the projected LISA sensitivity. And I have an example here of a plot in the case of the standard model effective field theory, which I'll explain more in detail what I mean when I say standard model effective field theory. But in this case, you can see that the predicted spectrum overlaps slightly with the LISA sensitivity, meaning that in some cases, we would be at least probing the area that would maybe give us some signal. And that hesitation, I don't mean it to be in a way a discouragement. Quite the opposite, actually. I think it's a very exciting area because we are at the early days of gravitational wave predictions. Like formalism, the uncertainties therein, the tool ecosystem, all of that is in a lively development status right now, where it's super fascinating to try to contribute or understand what people are doing. But what is true is that, LISA would probe some region. This region might be consistent with some scenarios where the electroweak phase transition was first order. So if we see something, we will be able to point out this looks like what could have come out from phase transition. Now, when it comes to the details, I have an example here of a very similar plot from what I showed you just in the slide before, also for the standard model effective field theory. But now I have two predicted spectra plotted here, and they correspond to spectra where the renormalization scale has been changed. So what it's showing is that the error bar or the uncertainty associated to the renormalization scale dependence, that in this case could give you either a spectrum that you're going to measure or something that you're not going to measure for the very specific same scenario. And while it's true that you can control this renormalization scale dependence to some extent, there's many other uncertainties, like, for example, gauge dependence, that are shown in this plot here, where all of the uncertainties are shown, where you have the difference between the peaks of the different spectra within the error bars divided by the minimum. And essentially what I want to illustrate with this, besides telling you that you have to read this paper, is very interesting, very enlightening in terms of giving the picture that, it's the early days, there's a lot to figure out. So it would be interesting to think whether there's a complementary way to try to understand the early universe phase transitions. Can we get experimental evidence from other places that can direct us into the areas and scenarios that might be interesting to develop and to develop calculational methods for? So this is a question that we want to answer in a little bit midterm of a research program, but what we started exploring in this paper. So before I tell you exactly what we did, let me tell you quickly about the first order phase transition, both in the standard model and then in the standard model effective field theory. And along the way, I'll explain you what I mean by standard model effective field theory. So in the standard model, you go ahead and you write down your leading order scalar potential with Higgs at finite temperature, and then you are careful with power counting, and then you calculate radiative corrections. And you end up with something, if you are careful enough, that looks roughly schematically like this. You have an effective mass term that makes your potential have a symmetric minimum here. Then you have a wall, but in this case, the wall will be generated by this phi to the 3 term that is radiatively generated, because at 3 level, you don't have a wall in the standard model. And then you have the quartic interaction of the Higgs picking up that potential and making it bounded from below for large field values. But for this to work out, you need a certain scaling of the Lagrangian parameters. You need a balance of these contributions in such a way that the potential actually looks like this. And this was something that Arnold and Spinoza worked out in the 90s. And they showed that the scaling that lambda has to follow is like gauge coupling to the cube. And what's interesting, and some of you probably already thought that, well, that's very, very small, and that's true, because in the standard model, the Higgs mass is proportional to lambda Beth squared, and in that case, with this scaling, you would never get a Higgs mass of 125 GeV. So, in other words, there's no hope for an electroweak phase transition in the standard model being first order. In other words, in the standard model, the electroweak phase transition cannot be part of the explanation of the matter-antimatter asymmetry. So what happens in the standard model effective field theory? So first of all, what is the standard model effective field theory? So first we ask ourselves the question of what if the standard model is an effective field theory? What if there's some beyond standard model physics at a higher scale that I cannot probe directly in experiment? What happens then? And then is there any way in which I can parameterize the effect of that heavy new physics in experiments that I can actually do? So the way formally that you proceed to do that is to write down the standard model Lagrangian plus higher dimensional operators made out of the standard model fields, and then you do an expansion in the VF divided by the scale of the new physics squared, and then you decide, what you want to explore. The first term in that expansion, would be the dimension 5 operator, the Weinberg operator in the standard model, but that's only one that you can write down. And then at dimension 6, you have a whole set of new operators. And in particular, here I'm writing down the ones that include only the Higgs boson, because they are the ones that are going to be relevant to understand when do you have a first order phase transition in the SMEFT. And then you have a lot of other operators that you can consider, but we will focus just on those in these three. And then you have these boson coefficients in front of them that have units of GeV to the -2. So once you consider this kind of parametrization of new physics, you don't know how this was generated exactly, what UV theory generated this, what particles you have to integrate out to get this. So given your model, your idea, you can always predict some values for these parameters that would then lead to deviations from the standard model. But what we can then write is we can write how the scalar potential looks like in the SMEFT. And the main difference here is that you're going to get a new term that goes like 5 to the 6 that opens up a very interesting possibility. That possibility is of having a negative quartic interaction, right? In that case, when you go at finite temperature, you have the same thing, that your temperature effective mass is positive. You have this minimum here, and then your negative quartic coupling at 3 level already is going to generate a wall, and your 5 to the 6 term is going to pick up the potential and make it bounded from below. And this is the case that categorically people have been studying almost always in the literature. Because it's a 3 level, you don't need radiative corrections. It's very nice. But what people figured out as well is that when you look at when a first order phase transition happens, when do you have the right equilibrium or the right contribution from each of these terms to get a first order phase transition, is exactly the region of parameter space that leads to a very small new physics scale below the TeV scale. So then the questions of, there's a question on the question, because our first assumption was that, what if we have some heavy new physics? And this is telling us, it's a first order phase transition in this case of lambda negative if your new physics scale is actually not high, like you said. So what about taking lambda positive and doing the same game as in the standard model? Well, this is exactly the case that we explored in our paper that has been to some extent neglected in the literature, and that we wanted to understand properly and see if it made any sense phenomenologically. So in that case, you have exactly the same that happens in the standard model with a wall driven by the 5 to the 3 term that gets generated radiatively, and to be able to figure out exactly how this looks, the actual expression is way more complicated than this. You need to do a proper gauge-invariant calculation in the SMEFT, taking your leading order potential. We only went up to leading order, and then figuring out what happens and when do you have a first order phase transition. Now, the cool thing about this case is that now you can actually, even though it's radiatively generated like in the standard model, you can have the Higgs mass as 125 GeV. And that is because the Higgs mass gets new contributions from these Wilson coefficients, and that leads also to a scaling for those Wilson coefficients consistent with that first order phase transition. So you can get the Higgs mass, you get some ranges of these Wilson coefficients that would predict the first order phase transition. But then the next interesting question is, well, what about all other experiments? I can tell you, well, these are the numbers, but what about precision test? What about, what is this region of parameter space of the SMEFT in terms of allowed and not allowed by experiment? So we did this in our paper, and we started by picking a point within a reasonable slice of the standard model, effective field theory parameter space, so the values for these Wilson coefficients, again, constrained only to the Higgs sector. And we did that by, seeing that there are some of them that, you can see very quickly that they're restricted by experiment. For example, corrections to the rho parameter would be proportional or dependent on this C phi d, and and then some back of the envelope calculation, more or less what region is allowed, and so on for the others. Then once you pick a point here, so the values for the Wilson coefficients, you find what lambda and m squared give you the right Higgs mass. And then we did two things in parallel. On one side, we calculated the likelihood of each point, doing a global fit using SMELI, a code that provides a global likelihood for precision constraints in the SMEFT. So this would compare against all relevant precision experiments and give you a likelihood. And we also checked whether the point led to a first order phase transition by implementing a binary search and finding the ratio of the BEF at the critical temperature divided by the critical temperature using this finite temperature potential calculated in a gauge-invariant way. And then we find points that then both agree with data and have a first order phase transition. And here are our results. The interesting thing here is that we have a pretty broad region of the parameter space that we have localized, that we know where it is, that is both consistent with experimental limits and that says there's going to be a first order phase transition. So even though we only turn on the Higgs sector operators, this is in a way the best case scenario to understand when a first order phase transition happens, and when you also get not a poor, even like a borderline exclusion, but actually a lot of these points get a pretty good fit, sometimes better than the standard model. So it's not that it's fringe data points, but we have a pretty reasonable region of the SMEFT that has a first order phase transition. And once we've done that, the interesting thing to look at is, we can actually start setting limits on whether the first order phase transition was first order, or whether the Electroweak phase transition was first order or not, by looking at colliders. And how does that go? Well, as I hopefully showed, this idea of a first order phase transition is driven mostly by this Wilson coefficient C phi, the one that comes multiplying the phi to the 6 in the potential. And a non-zero value for that, if we would have some heavy new physics contributing to that operator, it would also then shift the Higgs effective triple coupling, which has been measured already at the LHC, or at least setting limits to it. Like we see from this node, one can extract these limits, and then those limits can be compared to what we got in our paper. And you see that at least the LHC limits are perhaps far away from the limits that we found, in the sense that this is way broader than the region that we say, but already an extrapolation to what's going to be possible with the high luminosity LHC starts getting pretty close to actually setting a limit on the order of the Electroweak phase transition using colliders. So if C phi is constrained to be outside that region by whatever means, it means that the Electroweak phase transition cannot be first order if driven by heavy new physics. So just to end up my conclusions. So I hope I've convinced you that first order phase transitions are the most promising link between observations, cosmology, and particle physics, in the sense that we have a chance of getting a definite answer about what happened with the Electroweak phase transition. The SMEFT is a good agnostic proxy that captures the case of heavy new physics. Of course, this leaves out all the case of light new physics that has evaded all searches. This is not something we're treating, but still in that case, in the SMEFT case of heavy new physics, only the case of negative quartic interaction has been seriously thought about. But that also means that the new physics scale is too low, and you get into all this questioning the EFT formalism in the first place. So if you do proper power counting and gauge-invariant calculations, then you can show that the lambda positive window opens up, and then you have this region of the SMEFT that is consistent both with, as we showed with experiments, and a first order Electroweak phase transition, and that hopefully is not unreal to think of setting limits close to what we showed using future colliders. So I'll leave you with this excerpt from this excellent article, A Roadmap for the Future, that I encourage you to go check. And thank you.